Hi, beautiful darlings. We are going to do our notes on inverses today. So, inverse, if you think about that word, it kind of means the opposite or to undo something. That's what inverses are. To find the inverse of a function, it's a really easy process. It's 2 steps. The first step is going to be to switch the x and the y in the equation, and then the second step is to solve for that new y. Okay, so when I say my first step is to switch the x and y, if I'm looking at this first example, I don't see a y, but f of x is the same thing as y. So if you need to write that, go ahead and write that. So now my first step is to just switch those x's, the x and the y. So switching them is now here. X equals 2y plus 4. Our goal is to now get that y by itself. So to isolate that variable of y, I'm going to subtract 4 first. The x and the minus 4 do not combine, so it's just x minus 4 equals 2y. Now to get the y by itself, I'm going to divide by 2. 2 divided by 2 is 1, so I get 1y by itself. Everything over here gets divided by 2. You can leave your answer like this. I am not mad about that. Or you can divide each part by 2. So there's a 1 here in front of the x, so that's 1 over 2x, and then minus 4 over 2 can reduce to just negative 2. So that's also equal to the inverse. This notation, f to the negative 1 of x, right here, that's just notation for inverse. So we are now just telling the reader that we found the inverse of that original function, okay? And yes, I would love for you guys to try to use that proper notation, okay? So that's how we're gonna do it algebraically. We switch the x and y, and then we solve for y. What we're gonna do now is we are going to graph both the inverse, so what I just highlighted in blue, we're gonna graph that on this coordinate plane, and then we're also gonna graph the original function. So it says sketch f of x and the inverse on the same graph. So let's do the original inverse first. That has a slope of 2 and a y-intercept of 4. So I'm gonna start at 4, and I'm going to use my positive 2 slope. So I'm going to go up 1, 2, over 1, down 2, left 1, down 2, left 1, down 2, left 1, down 2, left 1. So here is the original function that we were given. And then we're going to sketch now the inverse that we found, which is a slope of 1/2 and a y-intercept of negative 2. So negative 2 is my y-intercept. And then I'm going to go up 1, right 2, up 1, right 2, up 1, right 2. You could also go down 1, left 2, down 1, left 2, down 1, left 2. When you make that line, you will notice that they intersect. That's okay. Inverses can intersect. Something that is a trait for the graphs of inverse is that their reflections over the line y equals x. So y equals x would have a intercept of 0 and a slope of a positive 1. So that's what I'm graphing here on this black dotted line. So if you remember back from geometry doing reflections over a line, if you were to take this graph and fold it on that dashed line of y equals x, you would see that the orange line would land right on top of the blue line. That's good. That means that they're inverses of each other, okay? Another way that we can graph the inverse, if I don't know the equation of them, is I can simply just switch the x and the y, just like what we did algebraically. So if you notice, for example, 2, I give you this function. I don't know what the equation is, but if I want to sketch the inverse, all I'm going to do is take these ordered pairs here, here, and here. Those are the only good points I see. So I see a negative 3, 0, a 0, 3, and a 3, 0. There are other points to pick all along here, but none of them are really like good points, you know? So those are the points I'm going to pick. And then I'm just going to switch the x and the y. So if this is x, y, I want to make the new point y, x. So that would be 0, negative 3, 3, 0, and 0, 3. If I plot those new points, 0, negative 3 is here. 3, 0 is still here, that's okay, and then 0, 3 is here. If I connect those dots in the same way, I now see that I have reflected over that line y equals x. And what was on the black graph is now going to land on that orange reddish graph, okay? So what they want to know is that inverse a function? Well, I can see right there it doesn't pass the vertical line test, so no, it's not a function. Now what we're going to do is find the domain and the range of both the original and of the inverse. So the original graph was in black from here to here. The domain would be from -3 all the way to +3, and the range would be from 0 to 3. Both of those are included. Now if I'm looking at that orange reddish, what we graphed for the inverse, the domain would be from 0 to 3, and the range would be from -3 to +3. You should notice that the domain of the original invert, or the domain of the original function, is now the range, and the range is now the domain. That is not a coincidence. If you are switching x and y for inverses, then that means everything switches for x and y. Domain are your x values, range is your y values, so you swap those. Okay, let's do it again. Here's the second function. Let's pretend that there's an arrow over here. So I see a good point here at 0, 5. I see a good point at 1, 4. And then I see another good point over here at 9, 2. So if I swap those points, that's now going to become 5, 0, 4, 1, and 2, 9. I'm not changing the signs or anything like that. I'm just swapping the order. So now I'm going to plot those points. 5, 0, 1, 2, 3, 4, 5 is here. 4, 1 is here. And then 2, 9 is here. So if I connect those dots, I see that that is now the inverse. Again, if you wanted to graph that line y equals x, you'll see that if I fold it on that dashed line, the black line would sit on top of that green line. So is the green line a function? Yes, it is. I can draw a vertical line anywhere on that graph, and it's only going to hit once. Okay. Domain of the original function, that's in black. That was starting at 0, going all the way to infinity. The range is from -infinity all the way to 5. The domain and range of the inverse. Domain is going to be from -infinity all the way to 5. The range is from 0 to infinity. Again, they have swapped. That's a good thing. If they didn't, we did something wrong. Okay, so inverse is all about switching the x and y, whether you're solving algebraically or doing the graph. Now let's go back and do some composition. So this is taking it back to Unit 1. So if you compose g inside of f of x and f inside the g of x, and both of them equal x, then that means they are inverses of each other. So if this is a true statement, then they are inverses. So for our first example, it says, here's f of x and g of x. Use composition to determine if they're inverses of each other. You have to check both. So let's say we do f of g of x first. That's going to be putting this g of x function inside of that x. So instead of 3x minus 1, I have 3 times all of that g of x function minus 1. I just replaced the x with the g of x function. Now I'm going to distribute my 3, which gives me 3x, oh, not 3x, sorry, 1x plus 1, and then the minus 1. Positive 1 and negative 1 cancel out, so that means f of g of x was equal to x. I am halfway happy. I can't stop here. I need to do the second part, right? So this is good. Now I need to check g of f of x. So this time, let me switch colors actually. This time, we're going to take the f of x function and put it inside the g of x function. So all of this is going to go inside that x right there. So instead of 1/3 times x, it's going to be 1/3 times 3x minus 1, and then still plus the 1/3. So again, I can distribute by 1/3. That's going to give me x minus 1/3, then plus 1/3. Those 1/3s cancel. I'm just left with x. So then that makes me happy for that one. So if both of them are just equal to x, then yes, they are inverses of each other. If one of them does not equal just x, then they're not inverses of each other, okay? To determine if something is inverses by the table, all you're doing is checking to see if the x and the y got swapped. Remember, f of x is the same thing as y. So if my points in this table were -2, -2, -1, 1, 0, 4, 1, 7, 2, 10, I'm just taking the x and then the y, it should be switched for this second table. So -2, -2, -2, -2, that's okay. -1, 1 became 1, -1, that's good. 0, 4 became 4, 0, that's good. 1, 7 became 7, 1, that's good. 2, 10 became 10, 2, that's good. So yes, these are inverses. Let's try it again. The point is 2, 8, 3, 6, 4, 4, 5, 2. You see what I'm doing? 6, 0. That's from the blue chart, x, comma, y. So if those got switched to 8, comma, 2, 6, comma, 3 in the red chart, this is blue. If this is red, then they're inverses. But look at this first one. That's 2, comma, -8, 3, comma, -6, 4, comma, -4. That's not what I'm getting or what I should be getting for the inverse. So these are not inverses. So no, not inverses. Okay. And then lastly is on a map. So if I give you the input and how it's matched to the output, you're going to swap that for the inverse, right? So if my input was -4 and my output was -2, for the inverse, it would be -2, output -4. Input of 0, output of -3 is going to be -3 to 0. The next one, 1 has an output of 2, so 2 has an output of 1. But 4 also had an output of 2, so 2 also has an output of 4. So that's the inverse. Now, is that inverse a function? No, because that input of 2 had 2 different outputs, and that doesn't make it a function, okay? So yes, this is a function, but this is not a function. That's inverses. Switch the x and y, either algebraically, on the graph, characteristically, whatever. That's inverses. Talk to you later. Bye.